so that you can get an idea of how to conduct the analysis after we are clear with the statistical principles and the theories about this basic design of experiments, right? Okay, so let me share my screen first. Okay, right. It is visible, right?
Yes, sir.
Okay. So as you see, as the topic goes, design and analysis of experiments. So first of all, we need to understand what is design of experiment and how it is important for any kind of research work. So generally, when we talk about data for conducting any research work, we generally have to data, right? Because once we have data, we can perform the analysis only in that kind of data. So this data, there are basically two ways by which we can obtain data. In some of the cases, the data may already exist. And in some of the cases, the data will not exist, but we'll have to generate the data. The first case is the case of a population. Suppose you want to do a study on the population of India. You want to find out what is the average poverty status in India, what is the average health status in India. So in that case, what happens is the population is already there. You just need to go to the population, fill a questionnaire, ask the answers, and then carry out the analysis. Then that kind of techniques are known as sample survey techniques. But in agriculture, what happens is in agriculture or whatever in a biological experiment, we do not have the data. So what we do is we generally develop a hypothesis or we develop a question. Okay, that there are certain varieties. Now we need to find out that which variety is performing better as compared to the other varieties. In that situation, what happens is the data is not there. So what we need to do is we need to plant those varieties in field or greenhouse or wherever possible. And then we need to look for the results that we are getting, the data that we're getting, and based on that results or based on that data, what we can do is we'll perform the analysis and we'll come out with certain conclusions or we'll come out with certain inferences. Now the question is how to carry out this experiment, or what is the layout of this experiment, or how can we perform this experiment in a systematic manner, such that all the statistical principles are fulfilled and such that the inferences that we draw from this data are statistically and scientifically viable. So this is something where the design of experiment comes into picture. So design of experiment is basically designing the experiment in a statistical or in a scientific manner so that the inferences that you draw from that particular experiment is viable in nature. Okay. So you see, so it is the basic definition is a statistical methodology used to systematically plan, conduct, and analyze experiments in order to obtain an accurate and a reliable experiment. Now, what is the main objective? The main objective is to minimize the amount of variation in the data while maximizing the amount of information that can be obtained from the experiment. So this is the main objective, that what we try to do is we try to minimize the amount of variation in the data. The amount of variation has to be minimized. Or in other words, the error has to be minimized. And at the same time, what we'll try to do is we'll try to maximize the amount of information that we can obtain from the experiment. Now, there are some of the steps of conducting a design of experiment. First is formulation of the problem. That is, the problem has to be defined clearly. For example, what is the objective of the experiment? Whether we need to find out which variety is the best, or we need to find out the interaction among the varieties, or we need to find out the effect of irrigation on the varieties. So the first objective, the first problem is that you have to define your objective, or you have to clearly state the problem that you are going to be solving. The second question is selecting the factors. The researcher needs to identify the factors that may affect the response and select the levels at which factors will be varied. For example, suppose I'm conducting an experiment using, say, 5 levels of irrigation or using 5 doses of fertilizers. So I need to identify the different doses which I think may have an influence on the response. The response may be the yield of the crop. So this is the second step, that I need to select all those particular fertilizers, and I need to also select the doses of the fertilizers which I think can have an influence on the yield or the response of the experiment. The third is designing the experiment. The researcher needs to choose a suitable experimental design, such as we can use a completely randomized design, we can use a randomized block design, or a factorial design, or a Latin square design, depending upon the experimental situation. Okay, so if there is no variability, we generally go for a completely randomized design. If generally there is a one-way variability in the experiment, we go for a block design. So a block design can be complete, it can be incomplete. So randomized block design is an example of the simplest example of a block design. Similarly, suppose if there are two sources of variability in the data. So in that case, what happens is we generally go for row column designs. So for row column design, the simplest design is a Latin square design. However, there are also other designs for row column designs. Now what we need, now there may be situations where we may have two or more factors and each may have different levels. For example, we are conducting an experiment in which there are 5 varieties of a crop, and also suppose there are fertilizers which are having again different levels. Or suppose I am conducting an experiment with fertilizers and irrigations. Now there are 5 doses of fertilizers or 4 doses of fertilizers, and there are also 4 doses of irrigations. So in that case, what happens is it becomes a factorial structure. It becomes a factorial design because we are having more than one factor. And again, each factor is having more than one dose or more than one levels. So the third question is we need to identify the situation. And according to the situation, we need to choose a suitable design that we need to use for carrying out the experiment. Then the fifth step is conducting the experiment. The researcher needs to carefully carry out the experiment and record the results. The sixth step is analyze the data. Now the analysis of the data will be done using statistical methods such as analysis of variance and regression analysis in order to determine whether the factors have got a significant effect or not. And the last stage is obviously the drawing conclusion. Based on the analysis of your data, we will finally draw a conclusion about the experiment. Now, there are certain terminologies we need to identify, we need to understand for performing design of experiment. First is an experimental unit. So an experimental unit is basically an unit on which the experiment is done, or the experimental material is divided into smaller parts. For example, a field is divided into different plots, and within each plot, we are applying the treatment. Then a plot may be an example of an experimental unit. Similarly, in case of an animal husbandry experiment, we are selecting different animals, and for each animal we are using treatment. Suppose a different feeds may be given to different animals, or different chemicals or different treatments may be given to different animals, or different injections may be given to different animals. So in that case, what happens is the animal is the experimental unit. Similarly, for human experiments, different doses of medicine may be given to different humans, right? In that case, the human in the experimental unit. So the experimental unit is basically the smallest part of the experimental material to which we are applying treatments. Next is an experiment. So an experiment is basically a way of getting question to certain answer to certain unsolved questions. Then we have treatments. Now treatments are the different objects that we are comparing in an experiment. In an agricultural experiment, we are comparing different varieties in order to find out which variety is working best in a given situation. So in that case, the varieties are the treatments. Or we are comparing different doses of fertilizers, or we are comparing different doses of irrigation. So that different doses of irrigation or different doses of fertilizers may be the varieties, maybe the treatments. For animal experiments, suppose there are 2 different breeds of cow. There is a Sahiwal breed, there is a Red Sindhi breed, and there is a Kangeam breed. So there are 3 different breeds of cows. Now we are giving the same feed to 3 different cows, and we want to find out that for a particular male killed, which of the breed is better, whether Sahiwal is better, or whether Red Sindhi is better, or whether Kangeam is better. So in that case, this breed is the treatment. Okay, so the treatment, the definition of treatment will depend upon the experiment we are considering. Okay. Next is a sampling unit. The object that is measured in an experiment is called a sampling unit. This may be different from now. Okay, so this sampling unit is from the factor. A factor is a variable category and definition. A factor can be fixed or random in nature. Now, sampling unit is basically generally it is same as the experimental unit. The object that is we are measuring in an experiment is called the sampling unit. For example, in an experiment we are conducting with 5 different varieties, and we are trying to find out the yield of the variety. So the dependent variable that we are measuring is the yield for each of the varieties. Then that particular yield is known as the sampling unit. So the factors are nothing but basically the treatments are the factors. A factors can be fixed in nature or a factor can be random in nature. Accordingly, the experiment can be fixed or random. Now, what is the difference? The difference is, suppose you have 5 different varieties. Suppose you have 5 different varieties and you want to compare only these 5 varieties. Okay. Then you conduct an experiment using these 5 varieties. The result that you get will be applicable only to these 5 varieties. You have another variety, the result from this experiment will not be applicable to the other variety. Then this kind of an experiment is known as a fixed experiment because the factors are fixed. However, there are possibilities. Suppose there are 100 varieties and you are not able to consider all these 100 varieties. Obviously, because you cannot plant 100 varieties, right? You will need a large amount of field. Your cost will go up. You cannot do that. So what we need to do is you randomly select a sample of say 20 varieties from these 100 varieties. But you want that in such a manner that these 20 varieties will comprise will be a representative of the entire population. And the results that you will get from these 20 varieties will be applicable to the 100 varieties as well. Then this kind of experiment is known as a random experiment and the factors chosen are random factors. So for both fixed effect and random effect, the model of experiments are different, the results are different, and the way of analysis is also different. For the sake of simplicity, in today's discussion, we will consider only fixed factors. We are not considering the random factors because random factors are a bit statistically and mathematically complex, and that will require a whole length of discussion. But for information, there can be situations like that also, where we have random factors, where there may be situations where we have both fixed factors and random factors. Then those situations are known as mixed factors. Okay. Now, replication is basically the repetition of the experimental situation. So what we try to do is we'll repeat the same experimental situation in order to find out an estimate of the experimental error. So that is known as a replication. Experimental error is something which you are not able to identify the result of the variation. For example, suppose I am conducting an experiment in a field with 5 varieties. Now, difference between varieties we know. Okay. There are 5 varieties, say A, B, C, D, and E. Now, A suppose produces an yield of 3 tons. B produces an yield of say 2.5 tons. We know that there is the difference between two yields that we are getting is because of using different varieties. But you will see that even if you repeat A, you are not going to get 3 tons in some other part of the field. Then there are some factors apart from the variety which are contributing to this difference, but I am not able to understand what is that cause of difference. Then that particular cause is known as the experimental error. It is the part of variation in the data which is not explainable or which cannot be explained using conventional statistical procedures. Then that is known as the experimental error. Okay. Sorry. Okay, now you see this is one example of a statistical design from G. Casella, Chapman and Hall. This is a book in 2008. Suppose some varieties of fish food is to be investigated on some species of fishes. The food is placed in water tanks containing the fishes. The response is the increase in the weight of the fishes. So this is my response variable. So I need to find out what is the increase in the weight of the fishes. The experimental unit in this case is the tank, because experimental unit is that part in which we're applying the treatment. So in this case, we're applying the treatment to the tank. So therefore, the experimental unit is the tank. As the treatment is applied to the tank and not to the fish. Note that if experimenter had taken the fish in hand and placed the food in the mouth of the fish, then fish is the experimental unit, as long as each of the fish got an independent scoop of food. Now, there are certain principles of design of experiment. There are basically 3 principles of design of experiment. First is randomization. Randomization meaning that you have to distribute the treatments randomly in the field to each experimental units randomly, because there are 2 purposes of randomization. First is you will get an independence of observation. Whenever you do randomization, there will be independence in observation, and independence in observation is required for statistical analysis. The second stage is you will be able to avoid personal biasness. Suppose I have created one variety. Okay, I have created one variety, say variety A. And I want to test this variety against 4 varieties, B, C, D, E. Now, I will generally have a biasness that variety A is better because I have created that variety, right? As compared to other varieties. So if I perform an experiment on my will, what I'll try to do is, without randomization, I will give variety A all the good treatments. I will take proper care of variety A. I will plant variety A in that part of the field which is most fertile. I will give maximum irrigation to variety A, and I will neglect the other varieties. So what will happen is, obviously variety A will give better results. It will have better yield. Other varieties will not have better yield, or they will have lesser yield. This is one case. So this is called personal biasness or system. So there are also other biases called systematic bias. So this personal biasness and systematic biasness can be avoided if we do randomization. That is, if we allocate the treatments randomly to the experimental units, and obviously independence of observations can also be achieved. Second is replication. Replication, I've already told, it is nothing but repetition of the treatments, of the same treatments, in order to provide an estimate of the experimental error. And the third part is local control. Now, local control, or it is blocking, basically is it is to group the experimental units into block so that the homogeneity is maintained, or so that the heterogeneity within the experimental field is maintained, is reduced. Sorry. Suppose I have an experimental field. Now, an experimental field is heterogeneous, obviously, because some part of the field will have a higher fertility gradient, some part of the field will have a lower fertility gradient. Okay. Whenever, suppose if there is a water runoff, I am providing irrigation from one end and it is stopping towards the other end. So obviously, whenever there will be irrigation, there will be seepage losses. This irrigation water will carry all the nutrients from one place and they will deposit at the other place. So correspondingly, from where the place from where irrigation starts, all the nutrients will get washed off and it will get deposited at the point at which the water stops. So the place where the water stops will have a higher fertility gradient because it is containing all the deposits of the nutrients. Just a minute. Meeting. पार्टिसिपेट करने के लिए ठीक है मैं कर दूंगा या तो है हाँ अच्छा ये उसका लिस्ट होगा थैंक यू थैंक यू Okay, so obviously in order to so see, obviously, so what happens is, so there are two kinds of fertility within the same field. एक जगह पे है जहाँ पे मेरा fertility बहुत ज़्यादा है, and there is one place जहाँ पे fertility बहुत कम है. So obviously, if I that varieties that I'll plant in those areas जहाँ पे fertility ज़्यादा है, they will be better. They will yield better, right? So how to tackle this situation? So this situation can be tackled by blocking or by grouping the experimental field. Now, if I block the experimental field into different blocks, okay, so this block is having high fertility, this block is having moderate fertility, this block is having low fertility. And then I will plant all the varieties in all the blanks. I will plant all the 5 varieties in block with higher fertility. I will plant all the 5 varieties in block with medium fertility. I'll plant all the 5 varieties in blocks with low fertility. Then I will see which variety performs better in all the blocks. Then that particular variety is the best variety. So this is how I can take care of the situation of homogeneity that is existing in the experimental field. So this particular grouping is known as local control, or it is called blocking. So these are 3 basic principles of design of experiments that we have to fulfill, or that any experimental design should fulfill, except CRD. In CRD, the third principle, this principle, local control, is not fulfilled. Now, why local control is not fulfilled? Because in CRD, what we do is we believe the experimental material is homogeneous in nature. And since we believe the experimental material is homogeneous in nature, therefore, there is no need for the fulfillment of the principle of local control. Although in reality, nothing is homogeneous. In reality, even greenhouses are not homogeneous. Pots are not homogeneous. Petri dishes are not homogeneous. So nothing is homogeneous. But in CRT, we generally tend to make a statistical assumption that the experimental material is homogeneous in nature. तो क्योंकि हम उसमें मानते हैं कि हमारा experimental material homogeneous है, तो इसलिए there is no need of local control. तो उसमें हम blocking नहीं करते, blocking की जरूरत नहीं है. बाकी जो दो प्रिंसिपल्स हैं, चाहे वो रैंडमाइजेशन हो, रेप्लिकेशन हो, ये सारे डिजाइन्स में यूज होते हैं. लोकल कंट्रोल सीआरडी छोड़ के बाकी जितने भी डिजाइन हैं, आरबीटी, एलएसडी, उन सब में यूज होते हैं. ओके. So by following these principles, we'll get better designs. So one of the techniques that we use to obtain in case of design of experiments is basically analysis of variance. So इसको हम ANOVA बोलते हैं. So analysis of variance technique was given by the famous statistician Sir Ronald Fisher. Ronald A. Fisher. He is also known as the father of statistics. So what is ANOVA? ANOVA is basically comparison of several treatment means. Now there is something known as hypothesis testing. You all guys must be familiar with. In which what we do is we use different statistical tests in different situations. Like if there are suppose two treatments, there are suppose two varieties, and I want to test. अगर मेरे पास दो ही variety, in that case there is no need to carry out ANOVA. We can do a simple Z test if there is a large sample. If there is a small sample, we can go for a simple T test. Okay, but whenever there are more number of treatments that we need to compare, we need to compare the mean effects of more number of treatments. Suppose there are 5 varieties. Whenever it is more than, then we need to, in order to find which of the treatments are significantly different from each other, the statistical hypothesis or the statistical test that we need to carry out is known as the analysis of variance test, and it is based on something known as the F statistic. Okay, this is something known as the F statistics. So here you see it is used when you want to determine if there are any significant differences between the means of groups based on variability observed within and between the groups. Okay. Now, okay, again there are different types of analysis. So this write-up has already been provided. You can read it in details. Obviously in lecture it is not possible to read it in detail because the time is less. The subject is huge. But you can again read it, and then if you have any queries, like you can ask. Okay, now again there are different types of ANOVA. There is one-way ANOVA, there is two-way ANOVA. One-way ANOVA is when there is only a single factor to be tested. Like suppose in case of your completely randomized design. In case of a CRD or a completely randomized design, you have only one factor, like the treatment. There is no other factors. So in that case, we generally go for a one-way ANOVA. Suppose you have two factors again. You have treatment and you also want to see the effect of blocks, or you want to see the effect of replications, or sorry, blocks. So in that case, we generally go for two-way ANOVAs. Then there are known as repeated measurement ANOVA. Repeated measures ANOVA is something which is generally used, particularly in case of medical experiments. What happens is you repeatedly take measurements. Normal design of experiments में क्या होता है? We'll take measurement only once. Okay, आपने एक experiment किया, आपने 5 varieties लगा दी उसमें, आपने सारे statistical principles कर दिए, blocking कर दिया, 5 varieties लगा दी, fertilizer वगैरह दे दिया. When will you measure? You will measure during harvest, because we are measuring yield. Okay, you will measure during harvest. So then what happens is we'll take the measurement only once. Now, if there is say only one factor, only variety, you go for one-way ANOVA. If there are two factor, variety भी देखना है, block effect भी देखना है, we go for two-way ANOVA. Medical experiments में क्या होता है? The subjects are humans, okay, or even say in animal husbandry experiment. And suppose I want to see whether a particular medicine or a particular drug has an influence on controlling the blood pressure or controlling the hypertension or not. So what I'll do is first I will measure the blood pressure of that person. Okay. Then I will give the medicine. I will again measure the hypertension of that person or blood pressure, both systolic, diastolic. मैं measure करूँगा and I will see. I'll tell him to take the medicine say continuously for 7 days. Again after 7 days, I will measure his blood pressure and I'll see whether there is a difference or not. Similarly for say sugar or glucose also. तो उसमें क्या होता है? I'll take repeated measurement. Repeatedly, I'll measure the same individual. Those situations में we need to find a different kind of an ANOVA that is known as a repeated measures ANOVA, because उसमें क्या होगा? direct effects आएंगे and residual effects भी आएंगे. So that kind of ANOVA is different. We go for repeated measurement ANOVA, and it is also there is also a specific group of designs called changeover designs or CODs, which are used in case of those kind of experiments where you have a chance of getting a residual effect as well as a direct effect, or where you can use a repeated measurement ANOVA. Okay, then there is again something known as MANOVA, multivariate ANOVA. Multivariate ANOVA is when you have multiple dependent variables and you want to analyze them. I told कि generally क्या होता है कि हमारे experiments में we have only one dependent variable, right? We have only say yield. But suppose apart from yield, you also want to consider panicle length for rice, or you want to consider the number of tillers, or you want to consider, say for horticultural experiment, you want to consider along with yield, you also want to check the canopy, how big the canopy is, or how tall the plant is, or how dwarf the plant is. So in all that situations, what happens is you have more number of dependent variables. So in those experiments, what we generally do is we generally go for a multivariate analysis of variance, that is known as a MANOVA, and we generally don't go for an ANOVA. Okay. So as I already told you, that ANOVA is based on an F statistic and it is a P value. Yes. Anyone wants to say anything? Okay. So ANOVA generally produces an F statistic. I also told you because it is an F test. And अगर हम softwares में करेंगे तो softwares में तो ऐसा F value नहीं आता, then we'll get a P value, which is the probability value. So the P value tells you the probability of obtaining an F statistic by chance error. So generally, if the P value is less than 0.05, then we'll say that there is a significant difference between the varieties or between the treatments at 5% level of significance. Okay, so that is the general thing that we do for agricultural experiments. In agricultural experiments, we generally use 5% level of significance. Medical experiments, we generally use 1% level of significance. Then we have to check the P value is less than 0.011. Okay. So this is a software. Earlier, what we used to do is theoretically, जब हम करते थे, then what we used to do is we used to calculate the F statistic. हम F statistic निकालते थे. Then F tables आते हैं, charts आते हैं, उससे हम मिलाते थे, and हम देखते थे कि if it is greater, then we'll say it is rejected. If it is less, then we'll say it is accepted. But now software has made lives easier for us. So we know there is no need to see F statistics chart and no need to calculate a statistic on Earth. Software सब कुछ करके देना. But here what we do is we do not get the value of F statistic. What we need to do is we just have to find out the P values. Okay. Next is something known as a complete and incomplete block design. So if the size of the block is equal to the number of treatments, or if we are applying all the treatments to all the blocks, then that particular design is known as a complete block design. Otherwise, it is called an incomplete block design. So generally, हम RBD करते हैं, RBD करते हैं, CRD करते हैं. These are all complete block designs, because in each block or in each replication, we will have all the treatments. But there are also situations in which it is not possible to have all the treatments in a block. So in that case, what happens is, suppose आपके पास 10 variety है, किसी block में 9 variety हो सकता है, किसी block में 8 variety हो सकता है, किसी block में 7 variety हो सकता है. Then those designs are known as incomplete block designs, where the number of treatments is less than the number of blocks. Okay. Please don't try to scribble on the screen. If you have any question, please ask, but please don't try to scribble or write something on the screen. Okay. So this is how we generally obtain a incomplete block design. Okay. So there are also situations of incomplete block designs. Like BIBD is an example of an incomplete block design. PBIBD may be example of an incomplete block design. Okay.
Excuse me, sir.
So, yes.
Excuse me, sir. Good morning, sir. Sir, I have
Good morning.
a question.
Yes.
So, can you clear the difference between, sir, ANOVA in regression and ANOVA in design of experiment?
Okay. So see, ANOVA and regression are two different things. Okay. ANOVA and regression are two different things. Regression we generally use when all the variables are quantitative in nature. मतलब there can be situations where the variable is quantitative or when the variable is qualitative in nature. Regression हम तब करते हैं, suppose आपके पास dependent variable, you have dependent variables and you have independent variables. Okay. Now this you have to understand linear model theory for that. इसमें क्या होगा, your जो independent variables है, those are quantitative in nature. Suppose you want to see the effect of temperature, rainfall on yield. Okay, now temperature will have a certain value, yield will have a certain value, rainfall will have a certain value, and you want to find out the yield. So in that case, you generally go for a linear regression model. Analysis of variance में क्या होगा, you are having 5 different, you are using treatments, right? So either a particular plant is receiving the treatment or it is not receiving the treatment. So it is a 1-0 situation. So your dependent variable is quantitative, but your independent variables are qualitative in nature. So because या तो एक plot में आप एक treatment apply कर रहे हो या फिर आप नहीं कर रहे हो. So it is a 1-0 kind of a situation. So जब ऐसे situations होते हैं, when the independent variable in design of experiment generally it happens in this way. The independent variables are qualitative in nature, but the dependent variable is quantitative in nature. Then we generally go for analysis of variance.
Okay, thank you, sir. And sir, please, please clear analysis of covariance in regression analysis only. This thing.
Analysis of covariance is, see, analysis of covariance is basically a combination of ANOVA and regression analysis. Okay. Analysis of covariance में क्या होता है कि you take a covariate. Now covariate का मतलब ये होता है कि there is certain variables which are also, उसको auxiliary variable भी बोलते हैं, which is having an influence on the main variable. It is highly correlated with the main variable. Suppose, for example, suppose in case of rice, I'll give you an example. In case of rice, if the panicle length is more, the number of grains will be more. If the number of grains is more, the yield will be more, right?
Sir.
Or if the number of tillers are more, the grain yield is again more. So you see this particular variable, grain yield, sorry, the number of tillers or the number of panicle length, or in case of wheat, the length of the ear, this is having an influence on the yield. It is highly correlated with the yield, but this is not the dependent variable. So what you can do is you can also introduce this variable in the your experiment so as to get more information. Okay, so another source of variation we came to know is the length of the panicle. Then what you're doing is you're introducing a covariate or you're introducing an auxiliary variable in the experiment so as to get more information about dependent variable. Then it is basically a mixture of your, because अब जो covariate आएगा, covariate is not having a situation of 0, 1, right? It is getting a dose or not. It is having a particular number. Okay, the length of the panicle, it will have a unit attached to it. Say this much centimeters. Similarly, the length of the ear, this much centimeters, or number of tillers. तो उसका एक number होगा. So you are having situations जहाँ पे आपके dependent variable में qualitative variables भी है, quantitative variables भी है, independent variables, and dependent variable में तो आपका qualitative है ही, quantitative है ही. Then that particular situation is known as an analysis of covariance. जब हम एक covariate ले लेते हैं या फिर एक auxiliary variable भी ले लेते हैं. Is it clear?
Yes, sir. Thank you, sir.
Okay. Okay, so next is a completely randomized design. So a completely randomized design, it is generally the simplest design that we have. And suppose there are V treatments that needs to be compared. This is one example that there are V treatments that needs to be compared. And all experimental units are considered the same and there is no division or grouping among exist. Okay, so generally I told you that the experimental material in this case is considered to be homogeneous. So there is no variation in the experimental material. So the V treatments are allotted randomly to the whole set of experimental units without making any effort to group the experimental units in a way of homogeneity. This design is very flexible because the number of treatments can have different number of applications. It is not necessary that RBD में क्या होगा कि सारे treatments का same number of applications होना चाहिए, because in every block every treatment has at least once, sorry, exactly once. सो सेम नंबर ऑफ रेप्लिकेशंस चाहिए, बट सीआरटी में दिस इज नॉट रिक्वायर्ड. आपके पास 5 वैरायटी है, पहले वैरायटी के आप 3 रेप्लिकेशन रखो, दूसरे वैरायटी के आप 4 रखो, तीसरे वैरायटी के आप 4 रेप्लिकेशन रखो. सो देयर इज नो हार्ड एंड फास्ट रूल कि सारे वैरायटीज के आपके सारे इक्वल रेप्लिकेशंस रखने होंगे. You can have unequal replications for different varieties. Therefore, this design is also known as it is also called a very flexible design. Okay, the number of replications for different treatments need not be equal, as I already told you, and may vary from treatment to treatment depending on the knowledge, on the variability of the observation of individual treatments, as well as the availability also. It also depends upon the availability. Suppose आपके पास treatment 1 ज़्यादा है, पहला variety ज़्यादा है ही नहीं, तो आप कैसे लगाओगे? So it also depends upon the availability. So this is they have given one example. Suppose there are 4 treatments and there are say 20 experimental units. You are having 20 experimental units and you are having 4 treatments. Now in this case, treatment 1 you replicated say 3 number of times. Treatment 2 you are replicating 5 number of times. So 8 हो गए. Treatment 3 you are replicated to 6 number of times. So 4 treatment is replicated 6 number of times, 20 minus. So this is how you can use a CRT. Now you see, so this is the reason that it is very flexible, because different treatments can have again different number of replications. There is no hard and fast rule के इतने replications ही होने चाहिए. Okay. Now all the variability among the experimental unit goes into experimental error. So when do we use CRT? CRT is used when the experimental material is homogeneous in nature. Number 1, particularly in case of greenhouse experiments. Suppose you have a greenhouse experiment or you have a lab experiment in which the experimental material is a petri dish or a pot experiment. Usually horticultures में हम करते हैं pot experiments करते हैं. Mango, you bring mango grafts or mango saplings and then we put it in pots. We do not directly field में नहीं लगाते. Similarly, जो microbiological experiments होता है उसमें जो हम bacterial culture करते हैं, that we do in a petri plates, right? Petri dishes में. या फिर जो greenhouse experiments होते हैं उसमें हम greenhouse में करते हैं. So in all these situations, what we believe is, we believe the experimental material is homogeneous in nature. It is not heterogeneous, because there is no variability in the petri plate, there is no variability in the pot, there is no variability in the greenhouse. So in all these situations, CRT is the most widely used design. CRT is often inefficient, okay, because it is the simplest design. There is only one source of variability. It is often inefficient. अगर आपका material homogeneous नहीं है, if it is heterogeneous and you are assuming it to be homogeneous, then the entire hypothesis is wrong. पूरा experiment ही गलत हो गया. Okay, so CRT is more useful when the experiments are conducted inside the lab. Now the reason is, whenever we have a lab-based experiment, we have greater control. जब भी हमारे पास lab-based experiment होता है, तो हम क्या करते हैं, हम ज़्यादा control कर सकते हैं lab-based experiments को. बाकी चीजों को फील्ड में तो हम इतना कंट्रोल नहीं कर सकते. लैब में हम टेम्परेचर भी कंट्रोल कर सकते हैं, हम ह्यूमिडिटी भी कंट्रोल कर सकते हैं, तो हम होमोजेनियस सिचुएशन बना के रख सकते हैं. वी कैन क्रिएट आर्टिफिशियली a homogeneous situation, which is not possible while we do experiments on field, right? And CRT is very well suited for small number of treatments and for homogeneous experimental material. This is what I told. So layout of a CRT. So how do you design the layout? So we divide the entire experimental material into areas of experimental units, say n. So there are n number of experimental units. And for the number of replications for different treatments in advance, no local control is provided. So suppose there are V treatments and they are numbered as 1 to V, and Ni is the number of replication for the ith treatment. So the first replication is, so first treatment is replicated n1 times, second n2 times, third n3 times, so on. जो मेरा V number of treatments है वो nv times मैंने replicate किया है, such that अगर मैं total summation निकल कर लूँ, सारा n1 plus n2 plus n3 plus nv करूँ, then that will be equal to my experimental unit, right? जैसे मैंने वहाँ पे दिखाया कि पहला ट्रीटमेंट हम 3 बार रेप्लिकेट कर रहे हैं, दूसरा ट्रीटमेंट हम 5 बार रेप्लिकेट कर रहे हैं, तीसरा ट्रीटमेंट हम 6 बार कर रहे हैं, चौथा भी हम 6 बार कर रहे हैं. So whenever I add all this, 6 plus 6 plus 5 plus 3, that is 20, which is the number of experimental units जो मेरे पास अभी available है. Okay, then what we do is we select n1 units out of this n units and randomly apply treatment 1 to this n1 units. Okay, जैसे suppose मेरे पास 20 experimental units हैं और मुझे पता है कि इनमें से 5 experimental units को treatment 1 apply करना है. So what I will do is I will randomly select 5 experimental units from these 20 experimental units and to these 5 experimental units I will apply treatment 1. Okay, तो 5 हो गए, अब बचे 15. इस 15 से मुझे पता है कि 6 ऐसे एक्सपेरिमेंटल यूनिट्स हैं जहां पे मुझे ट्रीटमेंट 2 देना है. सो इन 15 में से देन आई विल सिलेक्ट 6 रैंडमली. 6 यूनिट्स आई विल सिलेक्ट रैंडमली. अब रैंडमली आप कैसे भी कर सकते हो, यूजिंग रैंडम नंबर टेबल्स कर सकते हो, या फिर आप चिट्स यूज कर सकते हो, या फिर आप कॉइन टॉस कर सकते हो. आप रैंडमली 6 ले लोगे और फिर उस 6 में आप ट्रीटमेंट 2 दोगे. फिर जो बाकी बचा उसमें आपने ट्रीटमेंट 3 दे दी. सो दिस इज हाउ you calculate the you perform the layout and do the randomization in case of a completely randomized design or in case of a CRD design. Okay, so generally this is the model, and I'll show later on. This is the statistical model for the CRD. Yij equals to mu plus alpha I plus Eij. Yij is the yield, okay, from the ith variety in the jth experimental unit. Mu is the fixed effect, alpha I is the effect of ith variety or ith treatment, and Eij is the error component. Okay, और हमारा ये hypothesis होता है कि सारे treatments are equal. This is my null hypothesis, that all the varieties are equal. If there are v number of varieties, there is no difference between the varieties. And this is my alternative hypothesis, that there is at least any 2 varieties which are not similar, or there is a difference between any 2 varieties. And this is the layout. The data ऐसे arrange करते हैं, treatments 1 to v, and these are say y11. Y11 means treatment 1 in the or the unit receiving treatment 1 in the first experimental unit. ऐसे फिर हम calculate t1 calculate कर लेते हैं. T is this, and this is the analysis of variance table for a completely randomized design. So you see यहाँ पे there is only one source of variation, that is treatment, and then we have the error, and then we have total. So for treatments, since there are v number of treatments, so the degrees of freedom is v minus 1. Total is n, so degrees of freedom is n minus 1. So this is obtained by subtracting this from this. So n minus of v minus 1 is n minus v. यहाँ पे हम calculate करते हैं treatment sum of square, error sum of square, total sum of square. Then mean sum of square निकालते हैं, which is just this divided by the degrees of freedom. And then we calculate the f statistic. This f statistic is nothing but this divided by mean square error. पहले हम क्या करते थे जब हमारे पास सॉफ्टवेयर नहीं होता था, so we used to do everything by hand, and then we used to have one more table called f tabulated, जहाँ पे हम f table से f का वैल्यू निकालते थे, and if this value is greater than the tabulated value of f, then we used to say that this null hypothesis is rejected, meaning that there is a significant difference between the varieties. The varieties are not same. But अभी हम क्या करते हैं, because अभी हम I'll show you, जब हम सॉफ्टवेयर में करेंगे I'll show you in few minutes, in a while. अभी हम क्या करते हैं, we do it using p value, right? Software. So softwares में क्या होता है, कोई f tab तो नहीं आता है, but we'll get a p value. So and we'll see if the p value for this set treatments is less than 0.05, then we will say that this is highly significant. Okay. Now let me show you one example of this. CRT, one real life example. Okay, so this is one note that I have prepared for you all. Then how do you perform analysis in different softwares? I have mentioned the stepwise, and I've also given the codes. Okay, so you can just simply go through it, and you can simply copy it. I'll share this to the organizers, and then they can share it to you. So you can simply go through the steps, and you can simply just copy this code into your R package, and this will do. Okay, so this I have done for like CRD. I've also done it for post-hoc analysis. RCBT also I have done. And also I have done it for LSD. So you can just go through the steps, and then you can simply copy the code, plug in your data, and you will get the results. You can do it yourself. Now let us, I'll show you one. So see, this is one real life example that was performed to conduct this performance of 5 tomato varieties in a greenhouse. Now, because it is again a greenhouse, so therefore it is a homogeneous situation. So you see there are 5 tomato varieties: Thiliana, Ravi, Rashmi, Mahesha, and Bathia. And the dependent variable in this case is yield. And the yield is measured in terms of kg per plot. And each of the varieties replicated 5 number of times. Now, ये जरूरी नहीं है कि 5 टाइम्स ही रेप्लिकेट हो. इट कैन बी इवन मोर देन 5 ऑल्सो. ओके, मतलब कहने का मतलब ये है कि इट कैन बी अनइक्वल ऑल्सो, लाइक इट कैन बी 5 फॉर थिलियाना, इट कैन बी 4 फॉर रवि, इट कैन बी अगेन 5 फॉर रश्मि, इट कैन बी अगेन 3 फॉर महेशा, डिपेंडिंग ऑन the experimental units that you have in your hand for the experimental. Okay,
Dr.
now you
Banrjee,
see,
I have one question.
yes,
If the replication is not equal in all varieties,
yes.
then how we do analysis?
For a completely randomized design, we are not considering the effect of replication. जैसे हम ब्लॉक, जब हम आरबीटी करते हैं तो we are also considering the effect of blocks. In case of a completely randomized design, we are considering the situation that the only source of variation is varieties. Okay, so
डॉक्टर
this
बनर्जी,
varieties,
मैं चाहूंगा कि एक एग्जांपल, मतलब जिसमें अनइक्वल रेप्लिकेशन हो, तो उसको भी आप मतलब कि समझा दें, बिकॉज मेरे साथ ऐसा होता है, क्योंकि मुझे बहुत सारे जीनोटाइप पे काम करना रहता है, तो कभी कभी कुछ वाइल्ड एक्सेशन होते हैं जिसके सीड बहुत कम होते हैं, तो हम उसको
हाँ, हाँ.
2 रेप्लिकेशन या 4 रेप्लिकेशन नहीं ले सकते हैं, तो हम मुझे अनइक्वल रेप्लिकेशन जब करते हैं तो एनालिसिस में लोग बोलते हैं कि नहीं, इक्वल रेप्लिकेशन होना चाहिए, अनइक्वल को कैसे करेंगे?
नहीं, अगर आप कंप्लीटली रैंडमाइज्ड डिजाइन यूज कर रहे हैं, अगर आप सीआरडी डिजाइन यूज कर रहे हैं उस सिचुएशन के लिए, जनरली क्या होता है, जीनोटाइप्स के केस में हम ऑगमेंटेड डिजाइन यूज करते हैं.
ओके,
जब हम जीनोटाइप के एक्सपेरिमेंट्स
लेकिन
जो
वो
होते हैं उसमें हम ऑगमेंटेड
फील्ड में नहीं करते हैं, वो तो सारा लैब वर्क ही रहता है हमारा
तो लैब में
जर्मिनेशन।
अगर आप कंप्लीटली रैंडमाइज्ड डिजाइन यूज कर रहे हैं तो उसमें अनइक्वल रेप्लिकेशन का कोई इशू नहीं है, क्योंकि मैंने आपको अभी, जैसे मैंने अभी आप थियरी में दिखाया कि यहाँ पे हम आर मान ही नहीं रहे हैं, यहाँ पे हम मान ही रहे हैं कि ये ni है, कि जो पहला जो मेरा ये है वो n1 में जा रहा है, दूसरा मेरा n2 में जा रहा है, तो यहाँ पे हम मान ही नहीं रहे. जैसे इसी एक्सपेरिमेंट में अगर मान लीजिए मैं इसको कम कर दूं, ये 2 को मैं हटा दूं, कि मेरे पास 3 में, थिलियाना में मेरे पास 3 ही है, रवि में 5 है, रश्मि में 5 है, महेशा में मेरे पास 4 है, ठीक है. बथिया में मान लीजिए मेरे पास 2 है, अगेन 3 है, सॉरी ये है, तो भी मेरा जो एक्सपेरिमेंट का जो रिजल्ट है वो उतना ही वैलिड होगा अगर 5 में इक्वल में लूंगा तो.
ओके, एनालिसिस में सॉफ्टवेयर में कोई एरर नहीं बताएगा?
कोई एरर नहीं आएगा, कोई एरर नहीं आएगा. आपका जो डेटा फाइल होगा उसमें चेंज होगा. जैसे ये जो आपका एक्सपेरिमेंट है जिसमें मैं ये कर रहा हूँ कि मैंने 5 वैरायटी लिया है और 5 को मैं 5 रेप्लिकेट में दे रहा हूँ, तो उसमें क्या है कि डेटा फाइल आपको ऐसे बनाना पड़ेगा. मैं आपको डेटा फाइल लिखा, डेटा फाइल आपको ऐसे बनाना पड़ेगा. जैसे आपने वैरायटी ले लिया एक साइड में और एक साइड में आपने यील्ड ले लिया. अब क्योंकि हर एक वैरायटी के 5 रेप्लिकेशन है, तो वैरायटी 1 को मैं 5 बार यहाँ रेप्लिकेट कर रहा हूँ और यहाँ पे उसके करस्पॉन्डिंग यील्ड लिख रहा हूँ. सिमिलरली वैरायटी 2 को भी मैं 5 बार कर रहा हूँ और यहाँ पे मैं वो यील्ड लिख रहा हूँ. लेकिन अगर मान लीजिए आपके वैरायटी 1 के 3 ही रेप्लिकेशन, 5 रेप्लिकेशन नहीं है, तो आपका डेटा फाइल में ये 2 पार्ट जो है वो हट जाएगा.
ओके,
ये 2 हट जाएगा.
यस यस.
अगर ऐसे होगा. सिमिलरली मान लीजिए आपका जो थर्ड फैक्टर है, जो आपका थर्ड ट्रीटमेंट है या थर्ड वैरायटी है, उसके मान लीजिए आपके 4 एप्लीकेशन है, तो आपका डेटा फाइल में ये वाला पार्ट हट जाएगा, इसमें फिर 4 ही आएंगे.
ओके,
बाकी एनालिसिस प्रोसीजर में कोई चेंज नहीं सीआरडी के केस में. लेकिन आरबीडी के केस में ये नहीं हो. आरबीडी के केस में आपको इक्वल रेप्लिकेशन ही लगाने पड़ेंगे. अनइक्वल रेप्लिकेशन में आरबीडी वैलिड नहीं होगा.
इट्स वेरी यूजफुल, थैंक्स डॉक्टर बनर्जी. और एक मेरा, और मैं हमेशा कंफ्यूज रहता हूँ, ये इंडिपेंडेंट वेरिएबल्स एंड डिपेंडेंट वेरिएबल्स, कौन इंडिपेंडेंट होगा कौन डिपेंडेंट होगा, मैं मतलब हमेशा कंफ्यूज रहता हूँ. कुड यू क्लियर दिस थिंग्स?
देखिए जनरली क्या होता है, डिपेंडेंट वेरिएबल वो होता है जो दूसरे पे निर्भर करेगा. ठीक है, जैसे मान लीजिए आपका यील्ड जो है, हाँ एग्जांपल में बताऊं, जैसे मान लीजिए आपका जो क्रॉप यील्ड है, क्रॉप यील्ड विल डिपेंड ऑन अ लॉट ऑफ थिंग्स. ठीक है, क्रॉप यील्ड जो है वो आपका फर्टिलाइजर पे भी डिपेंड करेगा, वो आपका सॉइल क्वालिटी पे भी डिपेंड करेगा, वो आपका वैरायटी पे भी डिपेंड करेगा, वो आपका इरिगेशन पे भी डिपेंड करेगा, वो आपके सारी चीजों पे डिपेंड करेगा। तो ये आपका हो गया फिर डिपेंडेंट वेरिएबल। लेकिन जो आपका फर्टिलाइजर डोज है वो तो आपको, वो आपका चीजों पे डिपेंड नहीं कर रहा है, तो वो आपका फिर इंडिपेंडेंट वेरिएबल। तो जैसे मान लीजिए आप इस वाले सिचुएशन में हम क्या कर रहे हैं, इस ये वाला जो एक्सपेरिमेंट है, इस एक्सपेरिमेंट में हम यील्ड ले रहे हैं वेराइटीज का। तो यहाँ पे क्या है, जो ये यील्ड आ रहा है, इट इज डिपेंडिंग ऑन दी वेराइटीज, देन माय यील्ड इज अ डिपेंडेंट वेरिएबल। जनरली जो वेरिएबल हम मेजर करते हैं उसको हम डिपेंडेंट वेरिएबल बोलते हैं। लेकिन जो वैरायटी है, वैरायटी तो एक दूसरे से इंडिपेंडेंट है। चिलियाना का रवि से कोई रिलेशन नहीं है, रवि का रश्मि से कोई रिलेशन नहीं है, रश्मि का महेशा से कोई रिलेशन नहीं है। तो ये जो मेरे वेराइटीज है, ये वेराइटीज मेरी इंडिपेंडेंट वेरिएबल। लेकिन जो यील्ड है, यील्ड कहीं ना कहीं इन पे डिपेंड कर रहा है कि ये थिलियाना का यील्ड है, ये रवि का यील्ड है, तो मेरा जो यील्ड हो गया फिर वो मेरा डिपेंडेंट वेरिएबल।
जैसे मेरे पास 120 जीनोटाइप्स हैं और मैं डिफरेंट ट्रेड्स में ले रहा हूँ, लाइक जर्मिनेशन परसेंटेज, लाइक मीन जर्मिनेशन टाइम, लाइक परसेंटेज हार्डनेस सीड। तो मेरा जो डिपेंडेंट वेरिएबल है दैट इज जर्मिनेशन परसेंटेज एंड मीन जर्मिनेशन टाइम, और इनडिपेंडेंट वेरिएबल इज जीनोटाइप्स।
जीनोटाइप आपका
ओके,
जो चीज आप मेजर कर रहे हो, जैसे आप जर्मिनेशन परसेंटेज मेजर कर रहे हो, या मीन जर्मिनेशन टाइम मेजर कर रहे हो, या बाद में जाके आप सीडलिंग का लेंथ मेजर करोगे, तो ये सब आपका फिर डिपेंडेंट वेरिएबल होगा। और जीनोटाइप्स जो आपका है वो आपका इंडिपेंडेंट वेरिएबल।
ओके ओके। और आपने एक चीज बता रहा था कि इनडिपेंडेंट वेरिएबल अगर क्वालिटेटिव रहेगा और डिपेंडेंट वेरिएबल अगर क्वांटिटेटिव रहेगा, तो हम एनोवा करते हैं। तो इसमें कोई एग्जांपल दे सकते हैं क्या कि डिपेंडेंट वेरिएबल क्वांटिटेटिव और इंडिपेंडेंट वेरिएबल क्वालिटेटिव?
ये जैसे मान लीजिए यही वाला सिचुएशन लेते हैं, इसमें क्या है, आपका ये जो यील्ड वगैरह है ये आपका क्वांटिटेटिव है,
यस,
वेरिएबल, ठीक है। लेकिन जो आपका डिपेंडेंट वेरिएबल है यहाँ पे, जो कि आपका वैरायटी है, तो ये तो अब वैरायटी आपका क्या है, वैरायटी तो आपका नाम है ना। तो ये तो क्वांटिटेटिव नहीं है। जैसे मान लीजिए यहाँ पे मैंने उसको नंबरिंग किया है 1 2 3 4 ऐसे नंबरिंग किया है फॉर सिंप्लिसिटी, लेकिन इसको नंबरिंग इसलिए क्या है, ग्रुप करने के लिए। लेकिन वैरायटी तो यहाँ पे क्या है, ये थिलियाना है, ये रश्मि है, ये वो है। तो मेरा जो डिपेंडेंट वेरिएबल है यहाँ पे, दैट इज अ क्वालिटेटिव वेरिएबल।
यस यस,
इट इज नॉट अ क्वांटिटेटिव वेरिएबल।
थैंक यू सर। और सर एक आपने लीनियर रिग्रेशन एनालिसिस मॉडल में जो आपने बताया कि क्वांटिटेटिव और क्वालिटेटिव, तो वो उसका कोई एग्जांपल आप बताएं।
रिग्रेशन एनालिसिस जैसे मान लीजिए हम क्रॉप यील्ड फोरकास्टिंग करते हैं वेदर पैरामीटर्स के बेसिस पे, ठीक है। तो उसमें हम देखेंगे कि आज के लेंथ में हम यील्ड देख रहे हैं। मैं बहुत सिंपल बता रहा हूँ, ऐसे तो ये बहुत कॉम्प्लेक्स फेनोमेना है क्योंकि इसमें
राहुल सर,
वेट्स वगैरह लगते हैं। हाँ
हेलो, 1 सेकंड सर। आलोक सर, एक्चुअली हम लोग कल है ना रिग्रेशन पे क्लास है सर, तो उसमें हम ये सारे
नो कपिल, मुझे बहुत मजा आ रहा है और बहुत ही मतलब अच्छा ट्रेनिंग है ये, और आई होप कि मैं सारा डाउट्स मेरे क्लियर हो जाए।
नहीं हाँ सर, सब होगा। वो सेक्शन वाइज है सर, इसलिए थोड़ा सा
ओके ओके ओके,
हाँ ठीक है सर।
Sir, hello, sir.
Yes.
Yes, sir. Sir, in case of farmers' field, if fields are not arranged as a block, so this type of experiment we can apply CRD, sir. In case of farmers' field,
नहीं ना ब्लॉकिंग तो आपको करना ही पड़ेगा। फील्ड एक्सपेरिमेंट्स में यू कैन नॉट गो फॉर सीआरडी, बिकॉज फिर उसका मतलब नहीं है ना होमोजेनिटी। तो सीआरडी में यू आर एज्यूमिंग दैट द एक्सपेरिमेंटल यूनिट इज होमोजेनियस।
Okay. If sir 1 to 6 treatments are there, in every treatment 3 farmers are deployed, and also their field also. So in this case, we can apply.
You are taking, मतलब you are using different fields also.
Different fields, yes sir, different fields, different farmers fields.
उसमें तो फिर लोकेशन भी एक इफेक्ट है ना।
Yes sir.
हाँ, तो फिर वो that is a different situation. Then we go for groups of experiments, nested experiments. तो वो थोड़ा वो है एडवांस लेवल एक्सपेरिमेंट्स डिजाइन से,
Groups of
बिकॉज
experiments.
उसमें फिर क्या है कि उसमें आपका लोकेशन भी फैक्टर आ गया ना, लोकेशन ऑफ द लोकेशन भी तो चेंज हो गया फील्ड, then that is also a factor which will contribute to the differences in the values of yield or values in the response variable.
In this case, one-way ANOVA we can apply, sir. One-way ANOVA.
No, you cannot do one way.
Okay.
One way ANOVA you can do only when you have one source of variation. जैसे यहाँ पे मैं करूँ, यहाँ पे there is only one source of variation, that is variety. There is no other source of variation. उस सिचुएशन में आपका variety भी है, आपका लोकेशन भी है, then you cannot do one way.
Okay, sir. Thank you, sir.
Okay, so this experiment, this example is clear to everyone, right? So अगर आपके पास ऐसे example है, so you have to like the data has to be arranged in this way. Okay, now I'll show you how you can calculate this using R and how what are the inferences that you can draw. Just I guess R Studio सबके पास होगा. So first thing what we need to do is we just need to import this data. We can straight away import this data from Excel. You have to go to here, file, and then import dataset. From import dataset, you see from text reader, from Excel, from SAS, you can simply import it from Excel. Okay. Once you have import the data from Excel, it looks somehow like this. So this is the Excel file that I have imported over here, crd.xls. Okay. Now what I'm doing is I'm just this entire file, crd file, I'm replacing, I'm giving it a name. Okay. So I am given the name as data. Data is crd. So the crd file में जितना भी मेरा data था, that is stored in this variable now, data. Next, I am giving an option called head crd. So whenever I give head crd, this will show your data. So see, this is my data. There is variety and there is yield. Now what I need to do is I need to consider this variety as a factor, right? Because this is my treatment. So I can write treatment is equals to as dot factor. ये सब codes आपको available है, आपको मिल जाएंगे. I'm just showing it over here. Treatment is equals to as dot factor data dollar variety. So in this data, the variable that we have variety is considered to be as a factor or a treatment. Then when you write class treatment, this is the classifying variable. Then you see factor. So I have classified this variety or treatment as a factor. Next is results. So this results is just a variable. You can have any other variable. Is AOV. So this command AOV will give your ANOVA. So you see yield is depending only on treatment because there is only one variable. So this yield is a dependent variable. And then we have this symbol, this curl symbol, treatment, and then we are considering it for this data. And then you write summary results. And see, this is the analysis of variance table that you will get. So you have treatment and you have residuals. So residual nothing but error. And then now you see here you have the p-value. Now p-value, I told that if it is less than 0.05, then the results are significant. Now it is very less, e to the power minus 12. That is, ये 6 के आगे भी 11 zeros है. So it is very less. So you see here you have got this mark which shows that the treatments are significantly different. So there is a significant difference among the 5 parameters. Now you need to find out that which varieties are different from each other. अगर मुझे significantly difference नहीं मिलता, तो my analysis would have ended here. But now I can see that these 5 varieties are significantly different from one another. So now I need to check, okay, I need to do a pairwise comparison, which of the varieties are different from one another. So what I'll do is, I'll do something known as a 2K post hoc analysis. So I do a 2K HSD, and then you use results. So then you will get this table. Now you see, this is a pairwise comparison. Okay. You see here 2 is compared with 1, 3 is compared with 1, 4 is compared with 1, 5 is compared with 1, 3 is compared with 2, 4 with 2. So you have all possible pairwise comparison. you have the difference, you have the lower and upper values, and you have the p values. Now, depending on the p values, again, you can say that whether there is significant difference. Now, see, for 2 and 1, this p value is not less than 0.05. Thus, we can say that 1 or 2 में कोई significant difference नहीं है. Similarly, for 3 and 1, you see, it is less than 0.05. Thus, we can say that 1 or 5 में significant differences है. So, this is how you carry out a pairwise analysis for a CRD in R software. Okay, so this is a practical example. Okay, so the next analysis that we'll see is RBD. So this is about CRD. Okay. Now see, randomized block design, and an RBD, it is often also known as a
Excuse
randomized
me, sir.
complete block design. Yes.
Sir, I am having one question regarding the
Yes,
previous
please.
one that you were showing on R. Sir, I
Yes.
wanted to ask that when it showed the Tucky's a test, so we don't need to put that CD value over here, because maximum of the time in the table we have to put that CD value.
You can use CD value also. You can use CD. Actually, क्या होता है? There are a lot of post hoc analysis tests. Okay.
Yes, sir.
See, there is something known as LSD, least significant difference. Then
DMRT
there is something known as
also.
DMRT. There is something known as 2K stage. There is something known as bond. You can use whatever you want. If you use CD values, then you will use LSD. Okay. So you
Yes,
can
sir.
give CD values also. This is one method of post hoc analysis that I have shown.
And which one we
You can
should
use that.
use in which situation? Like
That is again, it is a very, sorry.
sir, in which situation we should use which one post hoc analysis? Like
Actually,
when
it
to
is
use
actually,
DMRT, Tucky's test,
I'll tell
or
you,
LSD?
I will tell you. Now there are different situations. Okay, there are certain, if there is a pairwise comparison, then you use certain thing. But it is again a very broad topic. You just do
Yes, sir,
one
because
thing.
I used to confuse regarding this, that
Yeah,
which
I'll tell
post
you one
hoc
thing.
I
You
used
just
to use.
it is again a huge topic. It is very difficult to like cover, because if I start explaining those things, then
Okay.
this today's lecture will go. I'll tell you one thing. In Google,
Okay,
you just write multiple comparison procedures, and then you write ISRI.
Okay, sir.
Okay. So once you write multiple comparison procedure in ISRI, you will get one, I guess, 20-page note is there. A PDF is there. And very easily it is explained like in different situations, which test you should use. You just go through that note once and you will understand.
Yes, sir.
When to
One
use
more
2K,
thing.
when to use DMRT, when to use Bonferroni, when to use बहुत सारे least significant
sir.
difference. You just go through that note.
And one thing, sir, in the previous one, you have showed in your that pair test when it was showing that 4:2 or 3:2. Yes. So there was in one
Pairwise
situation,
comparison.
there was p value 0.013 something, and it was significant if it is for 5% level of significance, right?
Yeah.
That's it only. Thank you, sir.
If it is less than 0.05, it is significant. If it is great at 5% level of significance, if it is less
Yes,
than
sir.
0.01, it is significant at 1% level of significance.
Yes, sir. Because for
question is-
agriculture sciences,
We use 5% level of significance.
yes, sir.
The question is you have to set what level of significance you want to see. If it is significant at 1% level of significance, it will obviously be significant at 5% level of significance. Okay.
Okay.
But the vice versa is not true. If it is significant at 5% level of significance, it is not necessarily significant at 1% also.
Yes, sir. Yes, sir. Fine, sir.
So you have
Thank
to
you.
select the level of significance for your experiment.
Yes,
And then
sir.
accordingly, using p values, you can calculate. Software में क्या होता है वो सारा देता है, वो 1% भी देता है, 5% भी देता है, सारा देता है.
Yes, sir.
So you have
And
to
in
select your range.
yes, sir. In one software, there is OP stat. They used to ask in the initial only how many replications. So in that situation, it is very difficult for us to tell different replications for different treatments, like for treatment 1, 3 replication, and for 2, 4 replication. So in that situation, it will be difficult, I think.
I have not used this software, OPStat.
Okay,
So
sir.
I'm not aware of it, because here generally we use two softwares, SAS and R, for statistical analysis, and also Python is also coming up, but that is more for machine learning. But generally we use SAS and R And
Okay, sir.
earlier people used to use SPSS. So that
Okay,
is also there. But OP-stat I am not, I have never used. I have not seen the software, so I am not.
Okay, sir.
Not
That is
aware of
by
it.
Hisar Agriculture University. So, okay. Thank you,
Not
sir.
aware of it.
Okay, sir. Please continue.
Sir, I have a question.
Yes.
Can you repeat the name of the note which you can find in ISRI website?
Yeah, you just multiple comparison procedures.
Okay.
Multiple comparison procedures, and then you write ISRI in Google, you will get the PDF.
Okay, sir. Thank you.
Excuse me, sir.
Yes.
So can you, sir, this is a simple question I want to ask. Can we calculate p-value for manually when we perform ANOVA and multiple comparison tests like that? Can we calculate p-value manually for things? Is there any
Manually,
procedure we
see,
can calculate manually p-value?
see why would you need to calculate? Why do you want to calculate manually when the software will give it to you?
Yes, sir,
Earlier,
software
what
is
happens?
there, but
Yeah, you can do, but in what happens is generally when you do it manually. So in that case, you cannot. We do not calculate p-value. There is nothing called p-value. Manually, में क्या होता है? You will get the f value in ANOVA table. You will have the mean square error for the mean square treatment mean square, and you will have the error mean square. Now what you do is you divide treatment mean square by error mean square. You get the f value calculated. अब क्या होता है?
Yes, sir.
अब क्या होता है? You get the f statistic, f value calculated. अब क्या होता है? ये जो f statistic होता है, this f statistic has got a statistical table. Okay. You have to see the value in that statistical table for 5% level of significance at a certain degrees of freedom. Suppose if your calculated value is f calculated you have got, and next you have to see the value of f at 5% level of significance at v-1 and n-v, that is the degrees of freedom for the treatment and error. वो degrees of freedom के लिए आपको देखना पड़ेगा f statistic if you have that table with you. Now in that table you will see that value. Now you see the calculated value and you see the tabulated value. If your calculated value is greater than the tabulated value, अगर आपका calculated value suppose 5 है और tabulated value आपका 0.5, then you can say that there is a significant difference between the treatments. This is the statistical procedure or this is the mathematical procedure जिस पे software based है. Okay, software भी इसी theory पे ही based. तो पहले हम ऐसे करते थे. Even I remember when we did our masters, the software तो था ही, like in 2015. But in order to understand कि कैसे होता है, our professors used to make us do in calculators. कि आप calculator में calculate करिए. So we should do in calculators. So this is the statistical principles. But क्या होता है कि there is no need ना. You need you have softwares. So one calculation will take you 2 hours. सारा total sum square निकालोगे, each observation को आप square करोगे, फिर आपको जोड़ोगे, and then you will divide it with degrees of freedom,
Yes,
subtract करोगे. One analysis will take you 1 day.
Yes,
And in
sir.
softwares, you will do it in 5 minutes. So what is the need to do it manually? Okay. So next is a randomized block design. So you see, if a large number of treatments are to be compared, then a large number of experimental units are required. Obviously, if the experimental unit is large, so you cannot do it in lab, right? Or you cannot do it in the greenhouse. So you have to go to field. Okay, when you go to the field, the experimental material is not homogeneous. Then what we can do is we can group the experimental material into blocks of size V. So generally, what happens is randomized block design tab use किया जाता है when there is only one way experimental variability. Okay, suppose you have a field and you know that there is a variation in fertility gradient in north-south direction. Then you do blocking in east-west direction, perpendicular direction. If there is only one way variability, then we go for a block design. Or block design maybe the simplest is a randomized block design. अगर two-way variability है, suppose आपके पास field है, excuse me, और फील्ड में आपका नॉर्थ साउथ डायरेक्शन में भी वेरिएबिलिटी जा रहा है, ईस्ट वेस्ट डायरेक्शन में भी वेरिएबिलिटी जा रहा है, उस सिचुएशन में आप ब्लॉक डिजाइन यूज नहीं कर सकते. देन आपको दो साइड्स में ब्लॉकिंग करना पड़ेगा, टू ब्लॉकिंग मतलब डबल ब्लॉकिंग करना पड़ेगा. आपको ईस्ट वेस्ट में भी ब्लॉक ड्रॉ करना पड़ेगा परपेंडिकुलर टू नॉर्थ साउथ, आपको नॉर्थ साउथ में भी ब्लॉक ड्रॉ करना पड़ेगा परपेंडिकुलर टू ईस्ट वेस्ट. देन दैट बिकम्स एन एग्जांपल ऑफ अ रो कॉलम डिजाइन, जिसको हम लैटिन स्क्वायर डिजाइंस बोलते हैं. But if there is only one way fertility gradient or only one way variability in the field, then we go for a randomized block design. Okay. So blocks are constructed in such a manner so that the experimental units within a block are relatively homogeneous and resemble to each other more closely than the experimental units in the different blocks. मैंने बोला ना कि आप क्या करोगे, आप फील्ड को ऐसे ब्लॉकिंग करोगे जैसे एक स्ट्रिप में आपका सारा हाई फर्टिलिटी जोन आ गया, एक स्ट्रिप में आपका सारा मॉडरेट फर्टिलिटी, सॉरी अच्छा, एक स्ट्रिप में आपका सारा मॉडरेट फर्टिलिटी जोन आ गया, एक स्ट्रिप में आपका लो फर्टिलिटी जोन आ गया. So you have to divide in such a manner that within the block, the experimental material is homogeneous. See, this is one example. You have V number of treatments, okay? And there are B number of blocks. So suppose the fertility gradient is in this direction. Suppose this way is the fertility gradient. Okay, then this particular area is low fertility. This is also low fertility. This is suppose medium and this is high fertility. So what I'll do is I'll do the blocking in this way. And then I will apply all the V treatments in this block. Now, usme kya hoga dekho? All these V treatments will be in low fertile block. Again, V treatments in say low fertile block. Now V treatments in say medium fertile blocks. Again, V treatments in medium fertile blocks. Again, V treatments in high fertile blocks. So we have all the blocks in which we have all the treatments. So this is how we generally go for blocking in case of a randomized complete block design. लेकिन इसमें क्या है कि वन वे फर्टिलिटी ग्रेडियंट, अगर आपका इस डायरेक्शन में भी फर्टिलिटी ग्रेडियंट है तब हम नहीं कर सकते, ये वाला डिजाइन हम यूज नहीं करते. तब हमें क्या करना पड़ेगा, तब हमें ऐसे भी ब्लॉक्स, अभी हमारा ब्लॉक्स भी बस ऐसे हैं, only we have blocks in this way. Then we have also, we need to also draw blocks in this way. Then we'll go for row column designs. Is it clear? So this is the crux of this one, randomized complete block design.
Dr. Banrjee, how
Yes.
we fix the replication in this design?
These are replications. These blocks are replications.
Oh, number of blocks is equal to number of replications.
Number of replications. In case of an RPD, this number of blocks is equal to number of replications. So this block 1 is nothing but R1. This block 2 is R2. This way it is the number of blocks. Okay. So this is how you arrange the data for say different blocks. Just annotations. Okay. So this is how you like for each block. So block 1, block 2, block I, block B. This is how you remove it for. So you arrange the data, and then you calculate the block totals. Here, if you calculate this, this will give you a B1. This is the total for all block 1, total for block 2, similar total for block B. There are B number of blocks. This is similarly here I'll get the treatment 1. The total of treatment 1 across all the blocks. So this is T1 is total for treatment 1, T2 is total for treatment 2, Tj is total for treatment J, and B is TV is total for treatment V. And this is the layout. Now how to perform the randomization? Now since here what we can do is we have to do randomization twice, because यहाँ पे हमारे पास blocks भी हैं and we have treatments also, so we have to do twice randomization. So first what we do is we find out the number of treatments 1 to V, sorry, and then number of units in each block is 1 to V, and then we will randomly allocate these V treatments to V experimental units in each block. In each block we will have V experimental units. So एक block में हमें पहले V experimental units randomly set करना पड़ेगा, and within that V experimental units हमें V treatments को randomly allocate करना पड़ेगा. This is the randomization. Second, for replication, I've already told you. In this case, the replication is equal to the number of blocks. So if there are B number of blocks, there are B number of replication. So the number of replication is equal because each treatment comes once in each block. So each treatment is replicated equal number of times. If there are 5 blocks, there are 10 varieties. Each treatment is coming once in 5 blocks. So each treatment is replicating 5 number of times. So total number of experimental units is 5 into 10, 50. Local control, I have already told you. This is the homogeneous blocks. That is local control. Now see, this is one example. There are 7 treatments which are denoted as T1, T2, T7, corresponding to 7 levels of a factor. Say there are 7 levels of fertilizer. There are 7 doses of fertilizer. And these are to be included in 4 blocks. So there are 4 blocks, block 1, block 2, block 3, and block 4. So one possible layout is this one. You see, here you see in each block, all the treatments are coming exactly once. So each treatment is replicated 4 number of times, because which is equal to the number of blocks. If you take one example, you see T1 is over here. Again, T1 is here. T1 and T1. So similarly, all the treatments T1 is replicated 4 number of times, which is equal to, I can say, equal to the number of blocks, that is B. So this can be a possible layout of an RCB design. Okay. So here we have a 2-way model, because in case of CRD, we had only treatments, but here we have 2 factors. We also have block. Block is also a factor because different blocks have different homogeneities, right? So here we have a 2-way model, and correspondingly the ANOVA will also be a 2-way ANOVA. So here you see we have the model can be written as Yij is mu plus beta I plus tau j plus Eij, where j I equals to 1 to B and j is equals to 1 to V. So Yij is the unit or the measurement from the ith block receiving jth treatment. Okay, so mu is the general mean effect, beta I is the effect of ith block, tau j is the effect of jth treatment, and Eij is the random error component, which we generally assume is distributed as a normal distribution with a 0 mean and a sigma square as a homoscedastic variance or a complete variance. Okay, constant variance. So, okay, so this is the, yes. Any doubts? Okay, so this is the analysis of variance table for the RBD. So you see RBD, we have sources of variation as blocks, treatments, errors, and total. Now, in case of blocks, there were B number of blocks, so the degrees of freedom is B minus 1. Treatments were V minus 1, so this is V. Total is V into B. Total experimental unit will be B into V, because there are V number of treatments, each replicating B number of times. So total experimental unit is BV, so minus 1. And this is simply obtained by subtracting these 2 from this. So BV minus 1 minus B minus 1 minus B minus 1 will give this. Similarly, you calculate the error sum of square, you calculate the mean sum of square, you calculate the F values. If the F values are significant, we can say the treatment is having a significant effect. If the F value for block is significant, we can say that the block is also having a significant effect. So this is an example of a RCB design. Let us see a real life example. So you see, this is one real life example of an RCB design. An initial varietal trial, late sown and irrigated, was conducted to study the performance of 20 new strains of mustard. So there are 20 new strains of mustard vis-a-vis 4 checks: Swarn Jyoti, ZC, Vardhan NC, Varuna NC, and Kranti NC. So these are the 4 check varieties out of 20 new strains, using a complete randomized complete block design at Bhatinda with 3 replications. And the seed yield in kg per hectare was recorded. So the seed yield is in kg per hectare. And this is how the data looks. I'll just enlarge it. Okay. So you see, these are the different strains, and they have given some code to it. And each, it is in 3 replications. Okay. And these are the different values that you are obtaining for all these 20 varieties, out of which these 4 are checks. This Swarna Jyoti is a check. Vardhan.
Sir, I have a question.
Yes.
We have different location, like 4 to 5 location, and different application, different number of genotype, then which design we will go through, CRD or RBD?
See, then it will be RBD, but there it is something known as nested RBD.
Because there is no
Okay,
equal number of replications, sir.
See, I'll tell you one example. Suppose what happens is, suppose you are conducting the same experiment at 5 different locations. Okay, you are performing an experiment. You are doing it in say somewhere in Punjab. You're doing somewhere in Rajasthan. You're doing somewhere in Haryana. You're doing somewhere in Maharashtra.
Yeah.
So 4 different locations you're performing the same experiment. So in that case, what happens is, your location hai aapka 4. These 4 different locations are also a factor.
Yeah.
Because you have to you need to also see what is the effect of locations.
Yeah.
So they are also a class, and the treatments are nested within these locations. So in that case, you have to use a nested RBD. Okay. You have to use a nested RBD design.
Okay, sir.
CRD you cannot use because आप तो field पे experiment कर रहे हो. So how can you use CRD?
Yeah.
Okay. So you have to use RBD. RBD में करोगे तो फिर location आएगा तो एक nesting factor आएगा तो इसको there is something known as groups of experiments. Okay, groups of experiments or multi-location trials. So this multi-location trial designs you have to use. As I told you, this design of experiments is a huge topic. It is a huge topic. So it is difficult to complete like in a day or in 1 hour or 2 hours. So then you have to use those kind of designs.
Okay, thank you, sir.
Okay. So you see, these are the different strains, and these are the codes, and these are the 3 replications for each strain. So each strain is replicated 3 number of times, and there are 20 strains. So 20 into 3, so total 60 experimental units are there. Okay. Let us see how does the data file look. So the data file looks somehow like this. Yeah. You see, this is the data file. So these are the varieties. And then you have the replication, and then you have the yield. So you have replication 1, and see in replication 1, you have all these varieties, and these are the yields. Okay. Similarly, for replication 2, you have all these varieties, and these are the yield. Similarly, for replication 3. So this is how you have to arrange the data. Okay. This is how you have to arrange the data. Next, what we do is, we as usual, I have told you, like we'll import the data in R using from here file. We simply go to import dataset from Excel. Okay. And then we can import. And what you can do is, while importing, I'll show you one small trick. There is no need to write code. While importing, suppose I want to import this data from Excel. Okay, so you browse over here, and my data is in downloads. So you want to import this data, RBD1. So once you import this data shows varieties, replications, yield. What you do is change varieties to character from here. Okay, change replication to character, because these are all qualitative independent variables, and yield is your dependent variable. So you change it to numeric. Once you do this, you select on import. Okay. Once you select on import, your data will be imported, and automatically our software will treat variety as character, replication as character, and yield as the dependent variable. It will automatically do that. So there is no need in CRD में मैंने दिखाया था कि I write a code that AS dot factor equal to. No need to write this code. Straight away you can do it from. Okay. Now once you import the data, then again the data is imported. So this is how the data looks after importing. Then what we need to do is we simply view the data, and then I just denote a variable called data in which I have stored RBD1. And then once I write head, I'll see this is obtained. This is how the data looks. In order to finding out the ANOVA, I cannot write AOV, I'll write LM. That is a linear model. So model is LM, linear model. Data yield. Now see, yield is dependent variable. and now it is depending on both variety as well as replication. CRD में मेरा ये वाला part नहीं था. It was just yield slash variety. Sorry, called variety. Here you see yield is depending on variety plus replication. Then I read ANOVA. I give out a covert. Sorry, ANOVA is model. And then on viewing ANOVA, this is the analysis of variance table that we get. Now you see in this table we have variety as one of the source of variation, replication or block as another source of variation, residual as another, the error part. And then these are the degrees of freedom. And here also you see it is highly significant. It is even significant at this one, 0.001. On the 0.1% level of significance may be a significant. So thus we can say that this is highly significant. And then again here, if you want to carry out post-hoc analysis, then it is a bit tricky. You have to install one package called Agricole, and after installation of that package, you have to carry out DMRT or LSD or something like that. It's a bit tricky, so I'm skipping that part right now. But again, you can find these things easily in ISRI website. There is something called Design Resource Server. You can easily find it over there. Okay. So this is how you calculate the RBD. Yes.
Sir, I have one doubt.
Yes.
Sir, the analysis you did, it was for just one trait. What if we want to do the ANOVA for number of traits such as 7 or 8 traits? Then what will be the coding for that?
You can do it separately. You can do it simultaneously. Okay.
Yes, sir, that simultaneously I want to know.
Simultaneously, then it is MANOVA. It is not ANOVA. It is multivariate analysis of variance. That is not ANOVA. It comes under MANOVA.
Okay,
if you do it separately, then this is the same code. I'll send you the code remains the same. But if you do it simultaneously, then there are more than, like there are n number, there are 7 independent variables. Then you need to do something known as multivariate analysis of variance. That is complicated. It is not that easy.
Okay, sir.
Hello, sir.
Yes.
Sir, actually, I was asking that replication is being showing here significant. So means like if the replications are also being significant, then can we do that? Means like can we analyze that whether the impact of the treatment is there or not?
I didn't get. See, treatment is significant, right?
Yeah.
Okay. Replication is significant. Replication is significant because there is replication significant. मतलब कि आपके experimental material में heterogeneity है.
Yes.
Okay. Heterogeneity उसके लिए आपने blocking किया है, तो different blocks के बीच में differences आ रहे हैं. That is because of the differences in the say soil variability or whatever it is in the different blocks. But you are not considered about the blocks, right? You are considered about the treatments.
Yes, sir. Yes.
You don't want to show which wala part is more fertile.
Yes,
you
sir.
want to show which variety is best. So what you need to do is you need to do for the treatment, carry out the post-hoc analysis for treatments. There is no purpose in carrying out the post-hoc analysis for the blocks. Suppose if it will show okay, block 1 and block 2 are having same, block 3 is different. Nothing is you are going to gain out of it, right? एक field में third block जो है वो सबसे fertile.
So I understand this one, but
your objective is which variety is the best. So you have to do the post-hoc analysis for the varieties.
Yes, sir.
उसके लिए आपको ये देखना है कि आपका variety significant आ रहा है कि नहीं.
Okay, sir. Then if the replication values are being so much like different from each other, like what I was asking, then whether we can carry out those like treatment replication impact on treatment will be...
you can do it. Actually क्या होता है, see, whenever we perform analysis of variance, so पीछे का जो statistical theorem होता है ना, वो ये होता है कि ये जो treatment sum of square है and जो block sum of square है, they are independent of each other.
Yes.
There is something known as the Fisher-Cochran theorem, which is generally used for carrying out the analysis of variance. Now, these things are highly mathematical and highly statistical, so I'm not going through those things. So उसमें ये कहते हैं कि हम जैसे जो total sum of square है, total sum of square को we are partitioning into treatment sum of square and block sum of square. तो उसमें क्या होता है, तो treatment sum of square and block sum of square are independent of each other. That means treatment effect and block effect is independent of each other. Block का treatments के ऊपर effects नहीं. हम blocking इसलिए करते हैं only to ensure homogeneity, ताकि ऐसा ना हो जाए कि एक हाई फर्टाइल एरिया में कुछ मिल गया, लो फर्टाइल एरिया में कुछ मिल गया, डिफरेंसेस ना. इट इज ओनली टू एंश्योर होमोजेनिटी. आपका जो ट्रीटमेंट सिग्निफिकेंट आ रहा है उसका ब्लॉकिंग सिग्निफिकेंट है या नहीं, उससे कोई इफेक्ट नहीं. आप सेपरेटली ट्रीटमेंट्स के लिए पोस्ट हॉक एनालिसिस कर सकते हैं, एंड यूजिंग दैट पोस्ट हॉक एनालिसिस यू कैन फाइंड आउट व्हिच ट्रीटमेंट इज सिग्निफिकेंटली गुड, एंड देन you can find, okay, these treatments are simultaneously okay, this is significantly different, and if that treatment which is significantly different is giving you the maximum yield, then you can say that this treatment is best out of all the 20 strains of variety that has been chosen.
Okay, sir. Okay, sir. I understood.
Okay, so this was all about analysis of variance for RBD. Then we have something known as the Latin square designs. So a Latin square design is it comes under a group of designs called row column designs. हम जैसे जैसे designs में आगे बढ़ते जाएंगे, so designs complicate होते जाएंगे. पहले CRT में हमने देखा कि CRT में कोई ब्लॉक नहीं है, कुछ नहीं है. RBD में एक ब्लॉक आ गया, Latin square में रो कॉलम्स आ जाएंगे, फैक्टोरियल में फैक्टर्स ज्यादा आ जाएंगे. तो जैसे जैसे हम बढ़ते जाएंगे, so it will become more and more complicated. So the treatments in RBD are randomly assigned to B blocks, such that each treatment must occur in each block exactly once.
Sir,
rather than assigning it. Yes.
Sir, while preparing input file, are need any particular format to import data from Excel?
In R?
Yes, sir.
In R, you can import data either in Excel format or in CSV format or in text format. So you have to save your data either in text form, or you have to save your data either in CSV form. CSV is comma separated variables, or you have to save it in Excel form. Through these three data only you can import in R.
Okay, so while entering data in a particular format in the Excel, so whether it require any particular format?
Yeah, it is there. It is required. I showed you, na. See, suppose this is for CRD.
Okay.
So this is the varieties and this is yield. So you write all these 5 varieties, 1, 1, 1, 1, and then yield. Similarly for 2, 2, 2, 2. So what we're doing is, you have to, this is the format by which we have to import it. Like you cannot write 1, 2, 3, 5, 1, 2, 3, 5. You cannot do that.
Okay.
Dr. Banrjee, like a randomized complete block design, we have also randomized incomplete block design.
Yes, incomplete block designs are also there.
So how we the data format is how we form data format?
See, incomplete block designs are of different types. Okay, randomized block design is one thing. Incomplete block design is a class. Incomplete block design ke andar you have BIBD, balanced incomplete block designs. You have PBIBD, partially balanced incomplete block designs. You have lattice designs. So there are many number of designs within an incomplete block design. So incomplete block design it varies.
Augmented design उसी में आता है क्या?
Augmented designs, हाँ, augmented designs उसमें आता है. Augmented designs दो मतलब complete भी हो सकता है, incomplete भी हो सकता है, दोनों हो सकता है. Augmented design में भी 2 टाइप होता है, टाइप A, टाइप B.
एक्चुअली वो जर्म प्लाज्म का हम लोगों का NVPGR से बहुत सारे प्रोजेक्ट चलते हैं जिसमें जर्म प्लाज्म को लगाना रहता है, तो हम लोग कंडक्ट करते हैं ऑगमेंटेड डिजाइन में ही. तो अगर हो सके टाइम हो तो ऑगमेंटेड डिजाइन को थोड़ा कवर कर लीजिएगा.
ऑगमेंटेड डिजाइंस तो मैंने नोट्स में भी प्रिपेयर नहीं किया, क्योंकि जो मुझे ब्रोशर मिला था उसमें CRD, RBD, LSD था बस, और फैक्टोरियल था.
नहीं सर, वो जैसे कि बाद में आप नोट्स शेयर करेंगे ना, तो जो भी
तो उसमें मैं ठीक है, मैं दे दूंगा.
एडमिनिस्ट्रेटर हैं उसको आप उसमें इंक्लूड कर लीजिएगा.
मैं आपको ऑगमेंटेड डिजाइन्स का एक PDF भेज दूंगा. और उसके जो है R कोड्स भी भेज दूंगा. ऑर्गेनाइजर्स को मैं दे दूंगा और आप लोग उनसे ले लीजिएगा.
हाँ, ऑर्गेनाइजर को दे दीजिएगा. थैंक यू डॉक्टर बनर्जी.
Okay, so if there are no more doubts in RBDs, then we'll move to LSD. So LSD में क्या होता है? See, there are only 2 factors, blocks and treatment effects, were taken into account. But suppose there are 3 factors. As I told, there is a field and both way there is fertility gradient in that. Then what we need to do is we need to divide that field into two ways. And then it is known as a row column design. Suppose I'll give you one example. Okay. Suppose this is your field. Okay. Up this way, me. Suppose this is north and this is south. So north-south, you have a fertility gradient. So as you move from north to south, the fertility gradient say increases. Similarly, either be east. This is east and west. Either also you have a fertility gradient. So अब क्या करना पड़ेगा? एक blocking हमें करना पड़ेगा perpendicular to this. So these are my blocks. Okay. And एक blocking करना पड़ेगा perpendicular to this. So this is another blocks. Now you see. So now this are nothing but my rows. And these are nothing but my columns. Now I have divided the entire experimental unit or experimental field into rows and columns. Now, how to perform the experiment? These field treatment varieties will be allotted in each row randomly and also in each column randomly. Then, and also the number of rows is equal to the number of columns. Then this becomes a square with V number of rows, V number of columns, V number of treatments. Therefore, it is known as a square design. And क्योंकि Latin letters use होते हैं, ABCD are Latin letters, so therefore हम इसको Latin square design बोलते हैं. So generally Latin square designs हम तब use करते हैं when there are two-way variability in the experimental material, and we need to divide the experimental material into rows and columns so that we are able to manage this two-way variability existing within the data. Okay. So you see one example of a Latin square. So a Latin square is nothing but it is an arrangement of order P, is an arrangement of P symbols or P treatments in P square cells, arranged in P rows and P columns such that each symbol occurs once and only once in each row and each column. This is very important. So each symbol will appear once and only once in each row and each column. So this is a 4x4 Latin square. So there are 4 rows and there are 4 columns. And again, there are 4 treatments. Now you see in each row and each column, each treatment appears exactly once. If you see A, you see in first row and first column, A is there only once. Similarly, in second row, second column, second row, you see A is there exactly once. Second column also, only once. Third row also, only once. Third column also, only once. And C. Everywhere in each row and each column, each treatment is appearing exactly once. So therefore, it is a square, and therefore it is known as a Latin square. One disadvantage of Latin square design is that everything has to be equal. Number of treatment has to be equal to number of rows, has to be equal to number of columns. And it is very difficult to maintain such a square field, a field which is exactly square in real life. So this is one disadvantage of Latin square design, but it is useful for carrying out analysis of variance whenever there are two-way source of variation. Okay. So now you see the model. Model थोड़ा और complicated हो गया because पहले हमारे पास बस treatment और block ही था, अभी साथ में row column आ गया. So this is something like yijk is mu plus alpha I plus beta j plus tau k plus eijk. I,j,k all 1 to v because square है. So all the treatments as well as the blocks as well as the treatments as well as the rows and the columns all are of size v or p. ऊपर वाला p था, whatever it is. So each of them are varying from 1 to v. So yijk is nothing but the response or the yield obtained from ith row, jth column receiving kth treatment. Okay, mu is the general mean effect, alpha is the effect of ith treatment, beta j is the effect of say jth row, tau k is the effect of say kth column, and eij is the random error component again. And this is how the ANOVA table looks. So we have rows, degrees of freedom is v minus 1, columns v minus 1, treatments v minus 1. Total is v square minus 1 because v into v square minus 1. And if you subtract this from this, if you write v square minus 1 minus v minus 1 plus v minus 1 plus v minus 1, you will get this. So similarly, we find out the sum of square errors for rows, columns, treatments, and error, total sum of square. Now you divide each of the sum of square by degrees of freedom, you get the mean square for row, similarly mean square for column, similarly mean square for treatment, mean square for error. And by dividing each of the mean square of error, you get the values of the F for R, for C, and for T. And again, depending upon the significance, you can say that whether the treatment effect is significant or the rows are significant, columns are significant. The rest of the procedure is same. So this is all about a Latin square design. Now Latin square design is also known as a complete design because you see the rows and columns are complete. Each row and each column is having every treatment. There are also situations of incomplete row column designs, but that is again a bit advanced. Like Uden square is an example of a design where we have the rows are complete but the columns are incomplete. Okay. Next we come to something known as a factorial experiment. So factorial experiments are also known as factorial design or factorial analysis of variance, but factorial experiment is not a design. Factorial experiment is basically an arrangement, or it is basically a setup. You can use a factorial experiment in a CRD. You can use a factorial setup in an RBD. You can use a factorial setup in an LSD. You can use a factorial setup in a BIBD. Factorial is not a design. It is simply an arrangement or a combination or a setup. Factorial experiment में क्या होता है कि we have suppose more than 2 treatments and each treatment is having more than 2 factors or levels. Suppose I want to study the effect of irrigation as well as fertilizer. Now for fertilizer, I have 4 doses. For irrigation, I have 3 doses. I want to study it together. So now you see there are 2 factors, fertilizers and irrigation, and each are having more than 2 doses. Fertilizers are also having 4 doses. Irrigation is having 3 doses, and I want to study them together. Then that particular experiment is known as a factorial experiment. So main advantage of factorial experiment is to investigate the independent and interacting effects. So now there are several advantages. One advantage is that the cost will be reduced. अगर हम separate experiment करेंगे तो उसमें cost ज़्यादा होगा. इसमें हम एक ही experiment में दोनों कर रहे हैं तो cost कम होगा. दूसरा है कि complex relationship अगर है तो हम explore कर सकते हैं. जैसे normally करेंगे irrigation और fertilizer का separate तो fertilizer का effect मिलेगा, irrigation का effect. साथ में करेंगे तो irrigation और fertilizer के बीच अगर कोई interaction है तो वो भी मिल जाएगा. तो ये advantage है. Disadvantage ये है कि थोड़ा mathematically complex होता है. It is a bit difficult, and again it is not like easy to draw the layout. Layout drawing थोड़ा मुश्किल होता है. So I'll give some example. So this, say the yield from different plots depends upon variety and type of fertilizer. Both the factors are in control of soil fertility. Now, soil fertility is not the factor I'm considering. This is just for blocking. So what we do is we assign it to different plots, keeping other factors like irrigation, fertilizer fixed, and the same for all plots. So I'll show you one example. See, 2 crop varieties denoted by small a and small b, and 3 fertilizer varieties, capital A, capital B, and capital C. Now these are the all possible combinations that we have. So this is the number of treatment structure. So you see, these are the all possible. So these are the possible arrangements. Okay, so B with A, B with B, B with C, A with A with B, and A with C. So we'll have 9 possible combinations. No, 6 possible combinations. 3 into 2, 6. And these 6 possible combinations can be arranged in this way or this way. So these are the treatment structure. Now this treatment structure, you can use it in an RBD, you can use a CRD, you can use an LSD, depending upon the soil conditions or the variability conditions. But this structure is known as a factorial structure. Okay. See, these are the possible arrangements that can be done.
Hello, sir.
These 6 treatment combinations that we have. Now, these 6 treatment combinations, we are using an RBD design with 3 blocks. So there are 3 blocks. This is block 1, block 2, block 3. And see, in these 3 blocks, we have used this 6 treatment combinations. In each block, each treatment combination will be there exactly 1. So this BA is over here. I can show it from here. So this is over here. It is.
Hello, sir.
Yes, any doubt?
Repeat please with CLD.
Repeat what?
No, sir.
Which part you want me to repeat?
Sir, factorial CLD.
Sir, we will provide the recording to every participant.
Okay, sir.
So, okay, so see, what I was trying to say is, in factorial, what you have is you have a treatment combination, right? So you had 2 varieties, small a and small b, and you had 3 irrigation, A, B, sorry, 3 fertilizer doses, capital A, capital B, capital C. Now what we're doing is we are considering all 6 possible combinations. So see, small a, capital B, small a, capital C, small b, capital A, small b, capital B, and small b, capital C. These are the 6 treatment combinations that we have. Now, these 6 treatment combinations, I am using an RBD design with 3 blocks. So these are 3 blocks that I have. So this is block 1, this is block 2, and this is, say, block 3. Now see, in each of these 3 blocks, I'm using these 6 treatment combinations. And we know that in RBD, each treatment combination will appear exactly once, right? So see, if I see BA, in first block also it is coming once. In second block also it is coming once. In third block also it is coming. And then the rest of the thing is same. Similarly, you will find out the ANOVA. But the ANOVA will be different in this case because here you have the mean effects and the interaction effects are also there. But again, like, it is not possible to cover everything. There is symmetrical factorial, asymmetrical factorial. It's also a very huge thing.
Can we take this in CRD?
Yeah, you can take it in CRD also.
Okay.
If it is a lab-based experiment, suppose if it is a lab-based experiment, suppose you have, say, 3 varieties. Okay, you have 3 varieties and you have 3 fertilizer doses, and you are doing the experiment in a greenhouse. You are doing it in a greenhouse where temperature conditions are normal, where carbon dioxide concentration is normal. Experimental material is homogeneous. You can do it in CRD. Okay, so we can estimate, as I told, that factorial is basically a combination. It is just the treatment structure. It is not a design. You can use CRD, you can use RBD, you can use LSD, depending upon the conditions that is available. So, see here, you can estimate the difference between crop varieties. So this is known as the mean effect for crop varieties. You can estimate the difference between fertilizer treatments, which is the main effect for fertilizer, and we can also find out the interaction between crop variety and the fertilizer. So this is the added advantage of using a factorial design. जैसे अगर normal होता अलग-अलग करते हैं तो सिर्फ crop variety का अलग से पता चलता है, fertilizer का अलग से पता चलता है. इसमें crop variety और fertilizer का कोई अगर interaction है तो वो भी पता चल जाएगा. Okay, now there is something called symmetrical factorial. अगर same number of levels है, जैसे 2 फैक्टर है और दोनों के लेवल से 2 है, तो सिमेट्रिकल होता है. अगर अलग है तो फिर उसको मिक्स्ड या फिर एसिमेट्रिकल बोलते हैं. Okay, so this is well about today's lecture. This you have to note. This is very important. That factorial experiments are conducted in the design of an experiment. So factorial experiment is not a design. It is done either in RBD or CRD or LSD. So this is about today's discussion. Remaining this lecture I have already shared. I will also share the R codes and the augmented design.
Can you
now,
say
if you have any
data format of Latin square design and Latin square design?
I'll show you it.
Data format of Latin square design.
Yeah, just give me 2 minutes. You see, this is one example of Latin square design. So an experiment was conducted at Agricultural Research Station, Maharashtra, Opurgaon, on cotton during the year this. using a Latin square design to study the effect of foliar application of urea in combination with insecticidal sprays. So there were 6 treatments. Okay. So T1 is control, T2 is 100 kg something, T3 is again at different location. Now see, there are 6 rows, 6 columns and 6 treatments. Okay. Now you see how they have arranged the data. Row, column, treatment, yield. So first row, first column, third treatment. This is the yield. First row, second column, 6th treatment. You see over here. T3. So first row, first column. So this is first row, first column, third treatment. First row, second column, 6th treatment. First row, third column, first treatment. This is how excuse me, you arrange it in the Excel file for LSD.
You please share all these data format to admin.
Alok sir,
Okay.
we will definitely share it.
Hello, sir.
After this session.
Yeah,
Hello,
I'll share it.
Okay.
Hello, sir.
Also,
I
you
have
can
a
find
question.
it. You can find everything over here. There is if you look for design resource server in ISRI website. So I'll just show you this thing to you people. You can just write design resource server on Google. Resources server. Sorry. You will get this link. Click on this link. You will be directed to design resources server. Here you go for analysis of data. Analysis of data. Here you will have all the designs. Most of the designs are over here. As you can see, RCB, incomplete correlation. Just click on RCB design. You will get the data, and you will also get the Excel file over here. Image Excel file, and you will also get analysis using SAS and SPSS. From here also you can do. Otherwise, if you want, I can also share.
Hello, sir.
Yes.
Sir, I have a question. In my PhD research program, a multi-location trial of some genotype is set up for 6 different locations, and the trait is to be evaluated is 8. So, which analysis I can use?
Are you going to analyze the traits separately or combinedly?
No, sir, combinedly.
Then you have to go for multivariate analysis of variance.
Multivariate, sir. Which analysis? AMMI?
ANOVA.
ANOVA. Okay, multivariate analysis. Sir, can you have the coding for R coding for this?
For MANOVA?
Yes, sir. For multivariate analysis.
You can find it in on the online. Otherwise, I'll share it to you if you want.
Okay, sir. Thank you. And the sir, set of data should be arranged in which type? The 6 locations. The data should be prepared on 6 locations separately or with the same Excel file.
First, पहले तो आपको वही करना पड़ेगा. Like first, you have to share it separately only.
Okay,
you have to prepare it separately only, and then you can combine it, you can merge together in one file.
Okay, sir. Okay, sir. Thank you, sir.
Hello, sir.
Yes.
Sir, how can we find the genetic variability parameters for different designs through R, like CV, heritability, genetic advance?
That does not come under design of experiment. For that, you have to study statistical genetics. Heritability is an entirely different thing. Genetic correlation is a different thing. Repeatability is a different thing. It does not come under design of experiment.
No, means sir, can we find it through R? Like
yeah, you can find it. You can find it. There are codes. You can find it.
Where we can find codes, sir? This site website we can find that.
You search on Google. Any more doubts?
बस वही है, ऑगमेंटेड डिजाइन को भी इंक्लूड कर लीजिएगा सर.
हाँ, वो मैं करके आपको जब शेयर कर दूंगा तो उसमें मैं ऑगमेंटेड डिजाइन भी शेयर कर दूंगा.
Sir, I have a doubt.
Yes.
Hello, sir. In case of factorial RBD, is there any limit in number of factors? For example, can we go for 4 asymmetrical factors?
Again, what happens is you can go for as many factors as you want, but क्या होता है, as the number of factors increase, your design is going to be very big, right?
Yes,
suppose if you have say 4 factors, okay, अगर चारों फैक्टर का दो भी levels हुआ, then it is 2 to the power 4, so it is 16 treatment combinations.
Yes, sir. Yes, sir.
If you have 3 levels, it is 3 to the power 4, that is 81 treatment combinations. अब जैसे जैसे आपका फैक्टर बढ़ता जाएगा या फिर लेवल बढ़ता जाएगा, आपका डिजाइन बहुत बड़ा होता जाएगा. अगर आपका डिजाइन बड़ा होता जा रहा है, if your design is increasing in size, then there are 2 problems. Okay. First problem is accommodating the design is difficult. You have to find a field which is large enough so that you can accommodate 81 treatments.
Okay, sir. Okay.
Number 1. Number 2 is as the size of the field increases, the size of the block will also increase. As the size of the block increases, it is difficult to ensure homogeneity within the block. Because if the block is smaller, you can guarantee that there will be homogeneity. But if the block is very long, then again there will be heterogeneity within the blocks, right? Because in that case, you cannot ensure that my block is very long. So my block is 100 meters long, and within that 100 meter, the entire soil is homogeneous. You cannot ensure that. Heterogeneity heterogeneity will be there. So to tackle those situations where you have large number of factors and large number of levels, and you want to go for a factorial setup, there are certain designs called fractional factorials.
Okay, fractional.
Okay, there are certain designs called fractional factorials. It is again some advanced designs where we do not take the complete factor, but we take a fraction of that. Okay, then again it is a bit complicated. Like we do not take full replication, we take half replicate, 1/4 replicate. These things are there.
Okay, sir. Okay. Okay, sir. Thank you, sir. Thank you.
Hello, sir.
हेलो सर.
Yes.
सर 2 ईयर के डाटा की सर पूल्ड एनालिसिस कैसे करें सर?
क्या चीज?
सर पूल्ड एनालिसिस.
पूल्ड एनालिसिस के लिए आपको वही ग्रुप्स ऑफ एक्सपेरिमेंट करना पड़ेगा. चाहे वो डिफरेंट लोकेशन, चाहे वो डिफरेंट लोकेशन हो या चाहे वो डिफरेंट ईयर्स के लिए हो, आपको पूल्ड एनालिसिस करना पड़ेगा. बिकॉज वो फिर एक नेस्टेड एनोवा बनता है, एक नेस्टेड सेटिंग बनता है. इसमें हम फिर ईयर्स के अंदर वो एक्सपेरिमेंट हो रहा है ना, तो ईयर आपका बड़ा फैक्टर है, उसके अंदर आपका जो एक्सपेरिमेंट हो रहा है वो छोटा फैक्टर है, तो वो फैक्टर के अंदर फैक्टर है. तो उसके लिए फिर नेस्टेड डिजाइन यूज होता है, नेस्टेड एनोवास बनते हैं उसके लिए. वो अलग टेक्निक है.
यस, थैंक यू सर.
Hello, sir. Hello, sir.
Hello.
Sir, I have a question.
Yes.
Sir, in CRD, I have 7 treatment and 2 concentrations are there.
7 treatment and 2 concentration. Each treatment is having 2 concentration.
Each treatment having 2 concentration. Then how we can?
Okay, you have so each treatment is having so 14 हो गया ना फिर तो. There is
Yes,
only
sir.
one factor, right?
Yes.
There
Sir.
is only one factor. Factor is only one, na treatment. Treatment is
Yes,
only
sir.
one, na. Suppose
Yes.
say you are having, suppose for example, give me an example. Suppose you are saying
Sir,
you are using nitrogenous fertilizers.
The pathological experiment is there. Mycelial growth.
Okay.
I give a treatment. Like a neem, datura, ginger, onion, and like these 7 treatment are there. And each treatment
And
like
each you are giving at 2 levels.
2 levels means 10% or 20%.
Then तो फिर वो हो गया ना. Then it is a factorial setup हो गया.
Then sir, I have used a factorial.
हाँ, it is a factorial setup only because you are having मतलब अलग भी treatments are different also, and each treatment is again having 2 levels.
But sir, you told that factor if more than 2 factor, 3 factor are there, then we have to use factorial.
इसमें 2 factor हुआ ना.
Okay, sir.
Neem is 1 factor, Dhatura is 1 factor, say whatever is 1 factor. Again in Neem also you are having 2 levels, na?
Yes, sir.
So that way you have to do.
Okay, sir.
One more question, sir.
Yes.
मेरा लैब एक्सपेरिमेंट है. मैंने यील्ड इंक्रीज करने के लिए 3 डिफरेंट ट्रीटमेंट लिया. उसके अंदर सर अलग अलग डोज है अलग अलग टाइम पे, तो उसके लिए कौन सा मतलब CRD अप्लाई करना पड़ेगा सर?
फैक्टोरियल होगा आपका टाइम भी एक फैक्टर आ रहा है उसमें।
यस सर, टाइम भी डिफरेंट है और डोज भी डिफरेंट है, अलग अलग
हाँ
वॉट
तो
पे
फिर
अप्लाई
आपका
करना है।
टाइम भी एक फैक्टर है, टाइम के भी लेवल्स है, डोज भी एक फैक्टर है, उसके भी लेवल्स है। ट्रीटमेंट्स तो आपके ट्रीटमेंट्स ज्यादा हो गए तो आपको फैक्टोरियल CRD लगाना।
ओके सर।
आप ये देखना पड़ेगा कि आपका वो सिमेट्रिकल होगा कि एसिमेट्रिकल होगा। अगर जैसे मान लीजिए टाइम के भी आपके 3 लेवल्स है, डोज के भी आपके 3 लेवल्स है, सबके 3 लेवल्स है, तो फिर वो सिमेट्रिकल हो गया। अगर अलग होगा तो फिर वो एसिमेट्रिकल होगा, फिर उसका लेआउट अलग होगा।
ओके सर, थैंक्स।
So if anyone still have any doubts, you can ask to sir. Okay then. So
Sir,
Yes.
sir, if you have any doubt regarding that, any software, any designs, we can contact any of these delegates letters, sir.
Yeah, you can contact anyone. You
Okay.
can contact anyone. You can contact Kapil, you can contact me, you can contact anyone.
Okay, thank you, sir.
So now we extend our sincere appreciation to Dr. Rahul Banrjee sir for their invaluable contribution to our training program. Their dedication, expertise, and exceptional presentation skills have made a lasting impression on all of us. So we consider ourselves fortunate to have had the opportunity to learn from such eminent professional. Dr. Rahul's presentation was not only informative but also highly engaging. So the use of real life examples and practical application help us grasp the fundamental principles with ease. They masterfully combined theory with interactive exercises, encouraging active participation and enhancing our understanding of the subject matter. So in conclusion, we express our heartfelt gratitude to Dr. Rahul Banrjee sir for delivering an outstanding presentation on the design of experiment. Their exemplary performance has enriched our training experience and empowered us with the necessary skill to excel in the field of data analysis. Thank you very much, sir.
Thank you very much. Thank you for having me. Thank you for inviting. Thanks. Thank you once again.
Thank you, sir.